Right. Okay, welcome again to the Machine Learning Coffee Seminar. Today we have a guest visitor, Professor Ray Pantine from Monash University, Melbourne, Australia. I don't know how many know Ray from before, actually quite many. So he's visiting for a couple of weeks or even more in the University of Helsinki, still till the end of this week. So you may be able to catch him there. So he's extremely well known on some early work on graphical models, and then after that, in particular on discrete non-geometric Bayesian things that some others have called topic models, and some very highly interesting, even more recent work, which I believe we will hear about today. Yeah. So many thanks for joining, Ray.
Fine. So this is my blog. Actually, it's a lure for PhD students. You know the story, right? You put some stuff up and just to attract PhD students. So, but you'll find any of my talks and slides and things up there. So, and so I'll have to do the arrow thing. Oh, that'd be difficult. So this is an old English rhyme. It's what a woman wears to her wedding. And I hope you're all thinking, what the hell? You know, why? So, yes. So, but this was actually the real title, and I didn't think that was appropriate for a conference. Venue is actually matching. This is me when I haven't shaved. You know. But these are a lot of the people doing the work. He Zhao is just completing. He did all the topic models. He's an amazing programmer who can do math, which is a great combination for machine learning. Landu's a long-term colleague. Ooh.
Changing slides.
It's got its own line. And Reza is our deep learning guru. So he's a natural language guy, and you should probably know the language guys went heavily deep learning about 5 years ago. It's the dominant paradigm because it works incredibly well. And we'll kind of look at that. But he's been coaching me on deep learning. By the way, this is an overview talk. So this is an overview talk. So I'll hint at some things which you'll get if you look into the references on the blog page. You'll see some of the related work. Just a background. Earlier this year, I was in a high-level meeting with a big professor of stats, who probably a lot of you use her software, way above me in ranking. And this discussion ensued. You know, how does she teach overfitting? She pulls out examples from machine learning, because of course I don't know how to do it. How do I teach overfitting? I pull examples out of statistics, because of course they don't know how to do it. That's our own thinking. I mean, I'm a Bayesian, so I've always had the view that a lot of classical statisticians don't really know. I mean, that's my biased opinion. Since then, I've started using stuff, so I'm no longer extreme in that way. I appreciate what they're doing, and I do a lot of their techniques now myself. But you know, so we had this discussion, and what comes out of it? Well, I realise we're both kind of we really have a lot to learn from each other, and that's the spirit in which I'm giving this talk. But the two communities here are the old and the new of machine learning. So what I'm going to do is a quick whip through. This is something old. What you'll see is the talk really does mirror this old rhyme. It just kind of came to me, you know. Oh God, that's what it is. Anyway. So the first thing is Bayesian network classifiers, which I've been doing. I started in 1990. Bit of a history there, actually. I was working at. I wrote my thesis up, ran out of money, and went to Glasgow, where I worked as a pre-doc. I don't know, it's a postdoc, but And the professor of stats there, Brian Ripley, who went on to become the reader at Oxford, he taught me Bayesian networks. So I was very fortunate to have him there. Because Bayesian networks, actually, they're very simple, and the inference is very simple. It's just if you read the papers, it looks complex, right? That's how a lot of that stuff. He explained it to me simply, and thereafter it was all easy. And you'd see these convoluted things afterwards, like that massive book by Collar and Friedman that just goes into intricacy that to me is kind of a bit silly, but anyway. So this is a Bayes network. I'm not going to go on about this. I hope you get the structure and the conditional probability tables. So we've got discrete variables, and there's just discrete variables within a table. This would be a tensor three-way if there's three variables, and so forth. Now, but we're looking at classification, and some time ago, the general framework was set up, in fact, by Neil Friedman. He was a Stanford guy who's one of these incredible geniuses. You know, you meet these people and you know, like Alex Smoller. I don't know, you meet these people and you know that they're a level above all of us. That's how it is. But he came up with this idea. If he puts the class variable at the root of the tree, then you can build a Bayes network classifier, and you can put a more elaborate structure down here. As long as this class variable at the root, you can do classification using Bayes theorem. And this is the naive Bayes classifier, the diagram. I hope, you know, this is the one thing everybody must learn in machine learning, a naive Bayes classifier. If you haven't done that, you know, you need to go back to school. That's all. So this is the KDB1. We have one other parent for each variable. We have two other parents for each variable. And this particular notation and structure came from Miran Sahami, who was actually a PhD student when I was teaching at Stanford many years ago. And a long time, 20 years afterwards, Jeff Webb's group, this is the Monash team, they set together a way of picking K, right? Here you can see there's K is 1, 2, 3, 4, 5. You go, how do you pick K? Well, they figured out they could do it really quickly with, this is one of those amazing things from the applied statisticians, leave one out, cross-validation. Again, if you don't know that, please go and learn. Fabulous stuff. Of course, you can't use it with deep neural network, but otherwise, it's very handy. Now, this algorithm, it actually works really well. It's really cool, but it doesn't beat the state-of-the-art random forest gradient boosting of trees. So you've got to think of, in classification, these are still very good algorithms. So deep neural networks works in certain contexts, but these are still, this one particularly is the king of the heap in classification. So they invited me, can you help us improve this algorithm? So I'm an old machine learning guy. I just use the standard two tricks I know. You know, I just apply them. One of them is better quality smoothing. Jeff's group, they're sort of applied machine learning people, so they're not sophisticated. They don't have Bayesian smoothing methods. As it turned out, we can actually use the leave one out cross-validation method here. For some reason, no one's thought of it before. I can't understand why. I'm not going to tell you about that here, but our current algorithm we're playing with is a leave one out cross-validation. Even though this paper here, that's a hierarchical Dirichlet method. We also added ensembling, which is a very old trick that we'll look at briefly. So a quick introduction to these. Why do you need hierarchical smoothing? I want to give you the idea. So red is the people with the disease. We're building a decision tree, test on a variable, get a different set of counts. These are the counts. And test on has gene male. We're left with 0 and 1. So what's our probability estimate here? You know, maximum likelihood 0%. You could lose a Laplace. There's very certain things. And this is what my statistical colleague was talking about. overfitting, here overfitting fails miserably. So what's our probability? There's various crude and simple estimates that the sort of the old style Bayesians might come up with, Laplace, an estimate, but none of them use the context. This is the context, the previous counts or the counts up above. How can we use that context? It turns out there's neat algorithms both using leave-one-out cross-validation and using hierarchical Dirichlet. So we put a Dirichlet here, a Dirichlet here, a Dirichlet here, and then priors. I won't go into that, but that's the paper we presented at ECML. Ensembling. So this is the most direct ensembling method. You come up with a set of hypotheses, you put your new data through all of the hypotheses, and you do the mean. So that's a simple ensemble. It's, by the way, it's, you got to, if you want to win Kaggle, you usually do an ensemble. That's just, it's been that way. Netflix was the same. Why does this work? This is an amazing formula. Now, this is another thing that everyone in machine learning must know, the bias variance formula, right? Gieman and Gieman, sort of 20 years ago. You've got to know this formula. We teach it very first time we can. But there's actually an extension called the bias variance covariance. And so if you had a set of hypotheses, there's a third term you add on. These guys, Guido and Nakano, they did this paper, kind of went by, no one noticed it, but Jiwa Zhou, the famous machine learning guy from China, he wrote a book on ensembles. And all the Chinese students know this stuff. So, because he's the big shot in China. So there's the justification. And what happens is, we want as many hypotheses in our ensemble as possible, because the more we have, we dilute the effect of the variance. But we want those elements in the ensemble to have a low correlation, because the more we have, we add a penalty term here, and as we have an ensemble of size 50, pretty much the entire mean covariance goes in. So we need low correlation, and lots of them as we can. So that's the classical frequentist argument for ensembles. Where I came up from at a completely different angle, we're approximating it as a Bayesian formula. We get the same formula, same idea, same intuition. It's this that we're coming from Bayesian statistics. This was my PhD thesis a long time ago. So, you know, Bayesian and frequentists say the same thing. Anyway, once we do this, I just realised I looked at the time. Once we do this, we beat random forests. With the ensemble, we actually beat gradient boosting, but only for discrete data currently, and now we're testing the continuous data. So it works really well. Topic models, quick whip through this. I'm going to assume people have a rough idea of what a topic model is. It's a version of PCA, but instead you're going to break this bag of words, and you're going to basically partition the words into types, what are called topics. Now it comes down to be a matrix factorization method, and there's loads of different matrix factorization methods. We do these, and these. We do all of these. Great fun. There's all different, you know, what's your data, what's your error measure? You know, you get a different method. And you can go deep neural net. You can shove in embeddings. An embedding is just another component more. There's nothing else. It's just and I've got this neat little. So if you want to read the terminology, components, topics, and embeddings. They're all the same thing. They just have different kind of context in their particular community. This is how they look. A face is broken up into bits. A document is bagged up, and then it's broken up. The words are partitioned. So the same idea, basically. So we looked at this and we thought, well, okay, well, we've got to improve it with some things. The first thing we're going to improve it is fixing up the priors. If you think of that matrix multiplication, we can put a prior on the rows. So when you draw a row, it's got to be from this particular, it's got to be sampled in a particular way. Oh, I deleted my slide there. I had an example of a Gaussian. So think of this as you're doing Gaussian clustering, but you're saying that all the clusters are equally likely and spherical. Equally likely is what you're saying. And if you've ever done SKDB or anything like that, the eigenvectors, the eigenvalues drop off exponentially. That's what you want. That's why you're using the method. And this particular technique doesn't allow it. So we want to set it up so it can allow the proportions to drop off exponentially. So that's what we do. There's a whole lot of research here. I'll still claim these guys didn't know what they were doing, apart from Tay. Little aside here, I've played with a lot of this code. You know, his was the only code that I couldn't make crash. So he's also the only one of the earlier guys who actually sampled his hyperparameters. Right? So UI Tay, as far as I'm concerned, he's another one of these gods, you know, who he writes fabulous code and it never, hierarchical Dirichlet processes, they're complex things. His never crashed. Everyone else's code crashed. About 5 other suites I got and tested. And also he sampled his hyperparameters. So none of my criticisms can apply to him. Anyway, this code is amazing because these guys, they just put this thing into mallet. They solved the problem that we were looking at, right? They did it in 2009, and then there's a whole stack of theory papers at NIPS between 2009 and 2012. No one noticed this. No one noticed this has basically solved the problem. Works 100 times faster, gives you better results on all metrics than anyone else's code, and it was kind of ignored. I emailed him in 2014 and him know, did you know about this? No, I didn't. So, you know, they didn't know they were solving this problem. It's a truncated method. Anyway, it's kind of fun. These guys actually did a pretty good job. They distribute code now. Pretty impressive what they do. So we put a paper in this, and I just want to describe something. This is what I call high fidelity. So these are the typical topics you get. So the content is obesity, overweight, in news. We've got 600 articles. These are the kind of topics you get up the top. But look at this, 1 in 1,000 words down the bottom. That's fidelity, right? You're isolating these word sets. We've got 100 topics from 600 documents. 80% of them are perfectly clear semantics. Right? That's fidelity. And actually, you know, Mallet does a moderate job of this as well. We're a bit better, but Mallet is pretty good at this too. And so we notice this fidelity situation. I'll flip through this so I can get to the rest of it. We also added word embeddings as a prior in the other direction. It's a bit more complex. I'm going to show you this. I just want to explain something. Multi-label learning. So this is an aside. Multi-label learning, well, we've got some data with different labels. So we'll change that around a bit. Different data, different labels. But it's going to be multitask learning, right? So we're going to build one giant classifier that does all of these tasks. And what we're going to find is that it's going to share knowledge and do a better job. Very intuitive, right? So here are our separate tasks. You know, this is our class variable, our model parameters. Here are our separate tasks all set up. But what we're going to have is a global parameter set, some local parameters, and of course some parameters that are only to the specific task. The idea is that there's enough data in here so that you get a reasonable idea of what these are, and then you can basically regress onto what these might be, because you've got enough data here. That's called hierarchical Bayes, and that's multitask learning in a Bayes-net diagram. We go another step. We're going to add some metadata to each of our tasks, and we'll now do a regression from the global parameter set, use regression from the metadata to get our local parameter set. And this is multitask learning, where you're also initializing the parameter set using metadata. This works really well. The statisticians have a name for this. It's called random effects models. Not that I know anything about that, but that's what someone told me. So we did this, we applied it to topic models, we put embeddings into topic models, works incredibly well. The software is MetaLDA from our brilliant coder. He embedded it into Mallet, but with our stuff. So it's pretty fast. Well, it's fast for what we're doing. All right, I'll flip some. What's amazing here is that we can take the standard topic that you get from all the other models, and you can break it up into parts using the embeddings. So you can subcluster the word, but this isn't based on data, it's entirely based on the prior. So it's kind of an interesting effect, but it works incredibly well, gives the best results of any. So why do these methods work? Quickly, partitioning, it's scalable, hierarchical models, that's a good idea, and ensembles, they're old ideas. Why do the topic models thing work? This factor analysis, random effects models, hierarchical Bayesian models. We use Gibbs sampling as a generic processing engine. And you've got to do it carefully, because some Gibbs samplers can be very slow. What I didn't tell you earlier, our Gibbs sampler for topic models beats most of the variational algorithms. Surprisingly enough, it does. Of course, they can run on, 4 gigabytes of data and get 200 topics really well. But I claim that's ridiculous, because if you've got 4 gigabytes of data, statistically, you should be finding 10,000 topics, not 200. And when you turn the numbers around, you'll find those systems screw up in any kind of challenge. Okay, something new. A quick look at this machine translation. So Reza is the brains. Poira is pretty smart. He's a top student coming out of, I think it's Sharif in Tehran. And I'm kind of along for the ride. Right, you get to do that with an old guy. And here's the task. The task is we want to do translation. But we're going to add these other tasks in and hope that by teaching named entity recognition, parsing, and semantic parsing, it's going to improve performance. So we add that to the system. How do we do that? Well, I already told you about multitask learning. That's all you do. So we just use the multitask learning setup. Here it is. This is how we do it. This is a recurrent neural network. Inside here, we break up the standard model, and these are our shared parameters. So these are the shared parameters. That's a task-specific parameter. So this parameter changes depending on what our task is. named entity recognition translation. These are shared parameters everyone uses. We tell it the task, and it's going to gate the output to modify. So it's going to use the general parameters, come out and use the task indicator to modify the output. So that's how you do the multitask learning. So it's a great trick. There are the parts according to my diagram. Works really well. Interestingly enough, their earlier version of this was doing adversarial, had an adversarial model. I always thought adversarial, you know, I was never that, being a sort of a Bayesian, I thought adversarial models were a bit funny. Anyway, it didn't surprise me that this particular task, we beat adversarial models. GANs are a different matter. It's sort of a dual parameter thing going here. All right, so active learning is another area where you can do amazing things, and it's one of the areas where both natural language and image processing are really getting fabulous results. And the task is, how do you select the examples? And we get some tasks we've got before, and we can actually generate traces and put learning in here. This is a paper I'm not going to talk about at this stage. Works very well. But there's some, I'm just blown away with what people do with deep neural networks. I've got to say that. Blown away. Incredible. So let's look at these things. Oh, yes, one more bit of result. Representation theory. Right, this is important. A bit of theory for you. So capacity theory. What's that? Simpler models are easier to learn. All right? Simpler models are easier to learn. Batnik, something or other mention, all that stuff. Regularization theory. We do a trade-off between the error and the model complexity. So there are these two theories that people have developed, both have a long history. Originally done in the 70s, this one. But here's the new thing. I got this from Andrew Barron. But there's a whole bunch of papers in the neural network community that kind of echo this thought. So this is a common term, right? This is our neural network sigmoid one layer, or two layer, neural network sigmoid units and a linear function. So this is the error term. This is the variance term. It comes from the variance part of that bias variance term. That's the variance term, and they're the same because they're just using general theory. So it's the same theory that gives you this kind of order. It's the bias term that's different. This actually can go to 1. This always goes to 0. This is the number of nodes in your network. So it always shrinks to 0. This one can actually go to a constant. I'll give you a hint. You want your error term, this is the mean square error. You want your mean square error to vanish. This can never vanish because there's a fixed bias term in there. So it'll never vanish, and this will. So in terms of representation, the neural net is winning. So how I like to say it is that deep neural nets are special. You know, they're special because they're actually better than linear models. All right, sorry. You know, that's a summary of Barron's papers. But there's a whole bunch of statistical papers on that as well. So why do these work? This is the one I get. This is the one I like to make fun of. They work because the PhD students don't need to learn statistics. And you know, I laugh, some people laugh, but you should see what happens with Resi students. You know, they're producing good results after 6 months. My students are going to spend a solid year learning Monte Carlo sampling because we have to do a lot of tricks to make things work. Augmentation, collapsing, we have to show them all sorts of tricks. But the deep neural guys, they're producing results, you know, really quickly. That's the difference. So it really is. Now, you may know that the guys who started this community, the founders of the community, they know their statistics. They're really good at it, right? None of the real innovators in this community are without statistics. It's, you know, whereas UIT now, he's a deep mind doing deep neural nets. No one would say that Wellman, who's at Amsterdam somewhere, is shy on statistics. All the really good people in deep neural networks are highly competent statistically. But nevertheless, in a lot of applications, people can do all sorts of amazing things. They've then got this great trick where they make it run at speed. Wow. And the deep models, you've just seen representation theory tells us there's real things you can do. And it's convolution structures and sequences. That's the kind of data where you need these things. So in any of our models where they're not really important, we usually win using the old methods. High capacity, and they do what I like to say, modelling in the large. You know, they're not thinking about, our students have to think about, well, if I change this one node here to something else, I've got to do a different sampler and what's going to be the effect. And so they're all doing this micro sort of analysis of all the bits. The deep neural network students, they just whack down some architectures, it's all in the architecture. Whack it down, shove in an atom optimizer, and bang, we've got there. It's not that simple. I wouldn't know actually, but you know. And they can do all of these other things that we could hardly dream about. You know, we could do some of these things, multitask learning. We could do them, but kind of poorly. They can do them really well, just by putting these components together. So machine learning in the large, it's amazing. All right, let's have a look at that. In the old, we needed experts to design things carefully. Our students needed a year of training. In the new, the algorithm part is pretty much done for you. It's put down on a GPU for speed, and it scales moderately well. Where into the small detail, they're really doing it in the large. Quite a difference. However, we get more interpretability. So the old methods get more interpretability. That's the key thing. I'm just, sorry at this stage, I'll just whip through these. So the new methods, there's a huge expansion in capability of what people can do. And that's why it's so popular in image and text. But they've lost some things. Interpretability, and there's whole classes of algorithms that seem to disappear. That I still think are pretty good, because in some of our stuff, we know they work well. I'll flip through this bit, something borrowed. Some of you may be familiar. This is my state-of-the-art graphics 25 years ago. I did this little, this is actually in a journal article I wrote. The idea is that you could automate statistics. Well, and that's all the deep neural network guys are doing, in a nutshell. This is, we can do this really well these days. There's people who are doing this, Stan. There's a local group working on Stan here at Alto. The Google guys have started trying to move into this area of TensorFlow probability. I haven't looked at it yet. Actually, there's a Tsinghua group, Tsinghua and the big university in Bayesian does this as well. I don't have that on the slide. So finishing is, we're actually into this currently. This is code we generate for traditional LDA. So we're going to regenerate all of He Zhao's algorithms using our software generator. And this is by Sachif. Oh, that's his first name. Good. He's, do you have any Sri Lankans here? No, probably not. Doesn't look like it. They've got the longest names in the world. So I cannot remember their last names, all I remember their first names. Anyway, finishing up, I'll flip through this. What we discovered when we looked at the models, I'll say this in a nutshell, we discovered that a lot of the topic modelling work wasn't up to scratch. The experimental methods weren't good enough. That's what we looked at. We're not saying that the deep neural network algorithms don't work well, because some of them are incredibly good, right? And what these guys are doing is sequences. So once you move into sequences, you should work better. So we're not criticising the method generally, we're just saying that their experimental work isn't quite as good as it should be. You know, that's part of the let many flowers bloom, the boom-bust cycle of machine learning, right? You remember the first edition of neural nets. There was a boom, and then stuff was done, and it busted for a decade, and now there's a boom again. So in the boom phase, we relaxed the experimental standards a bit. That's all that's happening. So things aren't all rosy. Anyway, here's my conclusion. I think the old stuff's pretty good. I don't think we should toss it out, and we're starting to work on techniques for automation, which actually started a long time before the deep neural network methods came in, but I think this has invigorated it, and now people are trying to merge the two, including Google. And NVIDIA wants to get into the act. They figure they want more, clients, right? And they just don't want to sell to machine learning people. They want to sell to everyone. So they're trying to broaden their scope as well. This is one area they're doing it. But why is deep neural networks fabulous? It's not because it works like the brain. It's because of hard technical details. The brain is the intuition, right? It's what gives us our insights into how these things work. But that's the intuition, but these are the reasons why everything works, according to my colleagues, right? According to my Monash Deep Neural Networks community. Finally, people shouldn't forget learning theory. And I have a different view of learning theory than a typical learning theory person in the machine learning community. To me, learning theory is optimization and probability theory. It's not VC dimension. That's just some bit of exotica. The real learning theory is optimization and probability theory, as done by the statisticians, the algorithmic people. Anyway, not to be forgotten. So that's it. Thank you. Oh, I've got another client. Oh, yeah, the NVIDIA guys. They're really pushing on to try to broaden beyond deep neural networks. So, there we go. Thank you. Oh, sorry. 10 minutes over. That's not to be expected. Sorry.
We still have time for questions, no worries. Any questions?
Yeah.
Yes. So a short question. You touched on it a little bit in the end, I think. But why should we, if deep neural nets are having this really good performance, why should we continue to work with probabilistic models? I like probabilistic models myself, but I mean, what would you say is like the main argument for doing this?
Additional potential. We do know that for things like sequences, convolutions, it's probably about the state of the art. There are areas where you've got simpler models, and some of the simpler areas, good old classification, we find all of these techniques are still working well. So basically there's algorithms which still work, and in some areas these other algorithms are still winning. It's just more a matter of broadening the set of capabilities. And GANs are a good example. In GANs, the way they currently do it, but you know, there are other methods we could try for GANs. People have to sort of explore them. So all it's really saying is the leading edge for deep neural nets is still playing around with the cost functions and trying to come up with techniques for dealing with overfitting. They're still, and trying to extend the model in useful ways, they're still the leading edge, and that leading edge is still probabilistic. It's still old school machine learning. And you look at the recent GAN literature, there are all these different techniques people are trying, Bayesian GANs, Wasserstein GANs, you know, they're all extending the simple deep neural network approach of GANs, adding in fancy tricks from the old school, and getting improvements. So I'd say that's an example of where to go. But in some areas, it's still the case we are getting better results. So good old classification, which is still very popular. Yeah.
Does you all have anything to offer for meta learning?
Yeah. So that's what we did it. We just had a regression inside. So your data for the regression is the model parameters at the task level. And then you can regress onto those model parameters from the metadata. So that's, we set that up with gammas and betas and polar gammas and all of our favorite distributions, and it works really well. So it's just a lot harder to do. And that was sort of one of my points there, is all of this learning to learn, meta learning, all of this stuff is a lot easier to set up when you've got your architecture. We think we can do similar architectures with some of our techniques, which is what we're doing now. So you can just put them in there and sort of crank a handle and get some results, but that's the thing there. That's one of the really interesting things. I mean, if you've been around machine learning, people have been talking about meta learning for decades, but they haven't really achieved good results with it. And it was really with the introduction of deep learning that it became a really powerful technique. And that the translation case is really interesting there, because it learns about word structure and sentence structure, and then it improves its translation with that. It's all very intuitive. Anyway, thanks.
So we have time for one more question. So what I've noticed is that in the deep learning, something that people don't talk about sufficiently is that they need to run a huge amount of cross-validation to set up the type of parameters, model selection, to structure a network and so on. And otherwise it really doesn't work well. And this is of course something that in probabilistic modeling has been worked on for decades. So do you have some take on this? So where would the deep learning go to fix this, or should they somehow fix this problem?
Their techniques are very brute force, so they're just going to have better and better techniques for nonlinear optimization. I don't see any magic answer to that. We do compilations of things, so you know we can embed the parameter learning as a Gibbs sampler and make it a bit more efficient. So And also there's no way they can do leave one out cross-validation. Basically the difference is exponential family models, which the old stuff works really well with, scales brilliantly, and you can do all sorts of cool tricks with it. Non-exponential family models, which means sequences, convolution, structures, and then you just, everything's brute force. So, you know, that's sort of, I don't think there'll be any wonderful. What they are, meta-learning, right? So that's the latest thing. There are all these meta-learning things applied to, what was it? I forget the task they're applying it to, but there's been a rash of papers last year and this year on meta-learning with deep neural networks. And they just have a bunch of tasks, and, you know, then the hyperparameters are set a model from the previous similar tasks. And that's you know, pretty obvious. How the hell do you get a paper out of that? But they managed to do it because it's deep neural nets. So yeah, that I think is probably the best technique. Meta-learning. So yeah, good question. Thanks.
Yeah, so many thanks. So now we are going for Christmas break or turn of the year break, and starting on the 14th, was it right? So that the schedule of the first 3 talks of 2019 is already on the web page. So thanks for the year, and many thanks very much.
Thanks for coming.